Okay, so section 9.3 is on the complex plane. So in section 8.7, we learned about complex numbers, and maybe you're wondering how this all relates to trigonometry and what we've been doing for the last couple chapters, and we'll see that in just a minute here. Okay, so what we're gonna do is we're gonna take a complex number, and in this section, they use a complex number is written in the form x plus yi. So in the appendix, they use a plus bi. In this section, we'll use x plus yi. Now, what about the z equals to part? Z is just so we can reference this complex number. So x plus yi, we're just calling our complex number z. Those of you guys who are moving on in your math careers, physics, engineering, anything like that, I would encourage you at this point to start practice crossing your z's. I know it seems silly, but in higher math, when you have x, y, and z in an equation, it's really nice to be able to tell that a z is a z and not a 2. So that's why you see mathematicians frequently crossing their z's. So if you want to start getting in the habit of that now, it'll make your life easier later on. So if we have a complex number, z is equal to x plus yi, what we can do is plot the number in the complex plane. And it's actually really simple. All we're gonna do is plot the point x comma y. Okay, so let me draw the complex plane. And again, hopefully you feel that this is really simple. So what we have is we have our good old XY coordinate system here. X we call our real axis. And you can see why, because X, when we have a complex number written in this form, X is the real part. Y we call our imaginary axis. And as you can see, when we have a number written in this form, the Y coefficient, that tells us our imaginary part. Okay, so let me put some numbers on here and then we'll plot some complex numbers. So the first one I'll plot is 2 plus 3i. Okay, so what I want to do is come up with the xy ordered pair that represents this point, and then we'll plot that. So x here is 2, y is 3. So all I have to do is plot the point 2, 3. So 2, 3, this is the point 2 plus 3i. We can see that since the x is 2, the real portion is 2, and since y is 3, the imaginary portion is 3. I'll color code some more points for you guys. Next one, let's do -1 plus 4i. Okay, so all we want to do is take the x and the y off of here. So x is -1, y is 4. So in order to plot this, we just plot the point -1, 4. So here's -1, 4. So this green point is the point -1 plus 4i. Let's do a couple more. How about 3 minus 2i? So again, what we want to do is pull off the real part, which is 3, and the imaginary part, which is -2, and we'll just plot that point. So 3, -2, this pink point here corresponds to 3 minus 2i. I got a couple more for you here. If I can find some more colors, let's see, I got a yellow and an orange. Fabulous. Next one, let's just do 4. Okay, so the number 4, help me out with this one. The real part is 4. What's the imaginary part here? 0. Okay, so if our real part is 4, our imaginary part is 0, that point just sits on the x-axis there. And any number that sits on the real axis does not have any imaginary component to it. Okay, so anything that's just on this real axis only has a real component and no imaginary component. Let's do one more. I know the yellow is hard to see. So let's do negative I. So what's our real component here? What should x be? 0, good. And then our imaginary component is -1. Okay, so on our graph here, that just corresponds to this yellow point, right? I know that's hard to see. X is 0, y is -1. So anything that lies on this imaginary axis only has an imaginary component and doesn't have a real component. Any questions on this? Okay, so plotting complex numbers isn't too difficult. The next thing we're going to do is work with 3 different forms of complex numbers. Okay, and this is where it will start to relate to trigonometry. So there are 3 different ways we can write a complex number. Okay, so different forms of complex numbers. We're going to see 3 different ways to write a complex number. The first is what we already saw. X plus yi is called rectangular form. Okay, so rectangular form is x plus yi. Anytime you see those x and y's, you should think that's rectangular. Okay, the next one we have is called polar form. Okay, so remember when we see these words polar, we should think r and theta, r and theta. And r and theta still mean the same thing that they did in the previous couple of sections. We're just going to apply it now to complex numbers. Okay, so, oh, and here we usually write z is equal to x plus y. So we have a complex number z. Okay, so what I'm going to do to write a complex number in polar form, I'm going to start with a complex number in rectangular form. Z is equal to x plus yi. Now what I'm going to do is I want to get rid of my x and y's and I want to substitute in things that have r's and thetas in them, right? Polar form is in terms of r's and thetas. So where I see this x, we know from the previous sections that x is equal to r cosine of theta. And where I see that y, we know that y is equal to r sine of theta. So, and then I still have this I on the end. Okay, I notice that both of these terms have an r in there. So I'm going to factor out the r and write this as r times cosine of theta plus I sine of theta. Okay, so this is a complex number in polar form. So this is a complex number in rectangular form. Here's a complex number in polar form. In this form, we have x and y filled in, meaning we might see 2 plus 3i. In this form, we have r and theta filled in. So we might see something like z is equal to 2 times cosine of pi over 4 plus I sine of pi over 4. Okay, so r and theta are going to be filled in. Anytime we have a complex number in polar form, it might not be specifically stated in the problem, but you should always, 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 always make sure that theta is in between 0 and 360 degrees, or if we're in radians, between 0 and 2 pi radians. Okay, so even if the problem doesn't explicitly tell you to make sure that your angle theta is between 0 and 360 or 0 and 2 pi, you should always do that. Okay, we have a third form of complex numbers. This is called exponential form. And it's based, I'll show you like a quick little teeny tiny proof and then I'll put it in a box. Okay, so this exponential form is based on something called Euler's formula. So Euler was a mathematician. You might remember that name Euler from the number E 2.71828 182.84590. That's Euler's number. He derived that number. So Euler came up with this other really amazing formula, the proof of which is way, way, way beyond the scope of our class, or beyond even the scope of any calculus class probably. So I'm not going to show you the proof or even discuss it, but Euler's formula says that e to the I theta is equal to cosine of theta plus I sine of theta. If we multiply both sides of this equation by r, what we end up with is exactly what we saw up here on the right side. Okay, so that means that exponential form of a complex number is r times e to the I theta with r and theta filled in. Our first example here, we'll work on plotting the complex number in the complex plane, and then we'll write it in both polar and exponential form. And we are given the complex number z is equal to 2 minus 2 root 3i. So this is a complex number in rectangular form. So here x would be 2 and y would be negative 2 root 3. So that's rectangular form. So the first thing we want to do is plot it in the complex plane. So our x coordinate, the real part, is 2. Our y coordinate is negative 2 root 3. So our point is going to be here. So what we want to do to get it in polar and exponential form, we need to find two things. We need to find r and theta. So remember, r is our distance from our pole out to our point. We need to find out what r is. And then theta is going to be our angle here. Okay, so first thing, working on polar form. Polar form is z is equal to r cosine of theta plus I sine of theta. And what we need to do with this polar form is we need to fill in r and we need to fill in theta. Okay, so we need to fill those two things in. So our formulas are the same as the previous sections here. R is equal to the square root of x squared plus y squared, which is the square root of x here was 2, y was negative 2 root 3. So 2 squared is 4. 2 root 3 squared, I'd have 2 squared is 4. Root 3 times root 3 is 3. So 4 times 3 is 12. So I get square root of 16, which is 4. Looking at our picture, we should ask ourselves if that is reasonable. Yeah, that looks about right. The next thing we need to do is find our angle theta. So to find theta, we know theta is equal to inverse tangent of y over x. Remember, this formula works if we're in the first or the fourth quadrant. Inverse tangent will only return the answer in one of these two quadrants. If we're in quadrant 2 or quadrant 3, we need to add 180. All right, in your calculator, make sure you're in degrees. Anytime you use inverse sine, inverse cosine, or inverse tangent, you need to be in degrees. Go ahead and hit inverse tangent of, you need these parentheses, negative 2 root 3 over 2. Your negative button's different than your subtraction button. Either it's a little negative in parentheses or you have a button that says plus / minus. Either way you do this, your calculator should give you negative 60 degrees. Now, this is really important. When we're looking for theta, you will almost always see the restriction that we want theta to be between 0 and 360. We want a positive angle. So our calculator tells us this angle is negative 60, but what we want to find is a corresponding positive angle. So if this is 60 and we know all the way around is 360, that means this is 300 degrees. There's also one other catch. When we're doing exponential form, which we'll get to in just a second, theta must be in radians. So what you're going to see on your homework is most of the time you're going to see theta in radians throughout this whole section because it's a requirement for exponential form, so it usually crosses over to polar form as well. So this is 300 degrees, but what we want to do is figure out what that is in radians. So 300 degrees, you can multiply by pi per 180 degrees, or we know this one well, right? 300 is 60 times 5. We know 60 is pi over 3, so this converts however you want to do it to 5 pi over 3. So that's what we should use. So polar form here is going to be z is equal to r. We want to fill in r. Cosine of theta, here I'm filling in 5 pi over 3, plus I times sine of theta, which is 5 pi over 3. The next thing we want to do is write this in exponential form. Exponential form is z is equal to r times e to the I theta. And we want to fill in r and theta. So filling in r and theta, we would get z is equal to, r was 4, and theta was 5 pi over 3. And we leave it just like that. Let's do one more. So same question, plot the complex number in the complex plane and write it in both polar and exponential form. And we have z is equal to -4 plus 4i. So this is given to us in rectangular form. This is the x, this is the y. So in rectangular form, we have -4, 4. So the first thing we'll do is plot that. So here's -4, here's +4. Here's our point. In order to convert it to polar and exponential form, we need to find two things. We need to find r, which is our distance from our pole out to our point, and we need to find this angle theta. So our formulas are the same here. To find r, we're taking the square root of x squared plus y squared. So we have the square root of -4 squared plus 4 squared. So 16 plus 16 is 32. Most of these problems are going to ask you to give your answer in exact form. So if you put this in your calculator, depending on the calculator, you might get a decimal approximation. What we need to do is recognize that 32 is 16 times 2. So this simplifies to 4 root 2. If you put this in your calculator, some of them will give you this and some of them will give you 5 point something, which is not exact form. So just be careful, exact form here, you need to leave it in terms of the square root. Next step is to find theta. We know theta is equal to inverse tangent of y over x, with one exception here. Remember, inverse tangent only returns an answer in quadrant 1 or quadrant 4. Our angle happens to be in quadrant 2, so if we're in 2 or 3, we need to add 180 degrees to whatever we get there. So we have inverse tangent of y was 4, x was -4. So make sure, again, your calculator is in degrees. You can go ahead and hit this one, inverse tangent of 4 over -4, or inverse tangent of -1. Your calculator is going to tell you -45 degrees plus 180 is 135. So let's look at our picture and make sure that looks correct. This angle, 135, yep, that looks good. Our r here is 4 root 2, yep, that looks good. So the important thing about having a picture is if you didn't have a picture and you just forgot about this 180, your calculator tells you -45, which is over here. That's clearly not correct. So the picture helps you remember, aha, I need to add 180 to bump that over. Okay, so we found r and theta. The next thing we should do is plug these into polar and exponential form. So polar form is z is equal to r cosine of theta plus I sine of theta, and we need to fill in r and theta. And then exponential form is z is equal to r e to the I theta, and again we're filling in r and theta. Okay, so some couple things to note.
is that typically you're going to be asked to give your angle in between 0 and 2 pi, and you're going to be asked to give it in radians. So the reason why we have to give it in radians is over here on this exponential form. This has to be in radians. It doesn't make sense to have a degree measurement as an exponent, although in polar form, either degrees or radians is allowed. Because exponential form has to be in radians, usually the whole problem will be in radians. So let's convert 135 degrees to radians. That is, of course, 3 pi over 4. And you might have actually identified that angle by looking at this picture. Since we know these two sides are both 4, this is our 45, 45, 90 triangle, which makes this angle 3 pi over 4. All right, so in polar form, we got 4 root 2 cosine of 3 pi over 4 plus I sine of 3 pi over 4. And in exponential form here, I have z is equal to r, which is 4 root 2, times e to the I times theta, which is 3 pi over 4.
So let's plot the complex number. In the complex plane. And write in rectangular form. Okay, so we have z is equal to 8 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. Okay, so the first question is to plot the complex number in the complex plane. Okay, so remember in our complex plane here, x is our real axis, y is our imaginary axis. So this is not in terms of x and y, it's in terms of r and theta, but we can still graph this in terms of r and theta. So in terms of r and theta, the first thing we want to do is draw in our angle, which is 2 pi over 3. So we know that's 120. That looks like this. Then we use r. R is our distance from our pole out to our point. So we draw on our point, and I label this with an 8. Okay, so this is actually the easiest direction. If we want to write this in rectangular form, we want to get it in terms of z is equal to x plus yi. So all we have to do is actually evaluate these two things. So we need to evaluate cosine of 2 pi over 3 and evaluate sine of 2 pi over 3. So evaluate, I mean get a value. So if you have your calculator with you today and you want to try punching this on in, feel free to do so. The first thing you need to make sure to do on your calculator is these are in radians, so you want to put your calculator in terms of radians. The other thing you want to make sure you do is when you type in pi, you need to use the pi button. You cannot type in 3.14. These should all be, so the question I had about the final was, since the final, you are not allowed a calculator, these ones we can actually do by hand, right? We know how to do multiples of pi over 3. So on the final, you might see something like this that you can do by hand. So cosine of 2 pi over 3 is -1/2. We know how to do that by hand or in our calculator. Sine of 2 pi over 3, that's square root 3 over 2. The next thing we should do is multiply this out. Whenever we put it in rectangular form, remember rectangular form is this form, x plus yi, so we want to get our answer to look like that. So I'm going to distribute this 8 to both of these terms. And so 8 times -1/2 is -4. And 8 times root 3 over 2, 8 over 2 is 4, so we get 4 root 3i. Okay, so this is rectangular form. Now this problem, we should check visually that this makes sense. So if we look at this triangle, we got that x was -4, and we got that y was 4 root 3. Yeah, that looks about right. If you wanted to check this, you could check Pythagorean theorem, but this looks good. Now this problem didn't ask us to put this in exponential form. And on your homework, you'll have some problems that don't ask you to put it in exponential form. They'll only ask you to go from polar to rectangular. But let's just get some brief review on this because we didn't do too many problems like this last class. If we were asked to put this in exponential form, oh, here, this one's rectangular. In exponential form, a complex number is z is equal to REI theta. And what we need to do is fill in R and fill in theta. And theta has to be in radians. So all we do is go up here to the polar form. This is R and this is theta, and we just plug them in. So in exponential form, this would be R was 8 and theta was 2 pi over 3. Any questions on this example? Okay, let's do one more. So same question, but now we'll do for z is equal to 7 times cosine of 210 plus I sine of 210. So same question. So we'll write the complex number in the complex plane, and then we'll write it in rectangular form. Okay, so the first thing I'll do is I'll plot it. So in order to plot a number that's in polar form, this is R, this is theta. We want to draw in theta, so 210, that's 180 plus 30 more. Here's 210. And then R tells us our distance from our pole out to our point. So this is 7. Okay, so there's our point. The next thing we want to do is convert this to rectangular form. So in order to convert this to rectangular form, what we want to do is evaluate. So find a value for cosine of 10 and sine of 210. So to do this, you can either plug these into your calculator, or we draw 210, drop a perpendicular. This angle's 30, so we know we have 1, root 3, and 2, and we can fill these values in by hand. You should get cosine of 210 is negative root 3 over 2. And sine of 210 is negative 1/2. Next step is to multiply this out. And since we're asked to put it in a rectangular form, that's always in the form x plus yi. So we do actually want to multiply this out. So we get negative 7 root 3 over 2. Oops. Sorry about this. I have minus 1/2 times 7, so that's minus 7/2 I. And we always write this in the form x plus yi. So you see I leave this I outside of the fraction. I don't put this into the numerator. So we always want in the form x plus yi. We should look at our picture and make sure that this makes sense. We got that x was negative 7 root 3 over 2. And y was negative 7 over 2. So that looks good. We could check with Pythagorean theorem if needed. I also have had students in the past, you are allowed a calculator on this exam, but you're not allowed one on a final. So if you had a question like this on the final, you can evaluate these by hand. So I don't want you guys to rely too much on your calculator. I have had students whose calculators you could plug in right from this step, and their calculator would spit out this step. Okay, so you're welcome to try that, but again, on the final, you're gonna need to know how to do these by hand, so make sure you learn that. Just for fun, let's list out the exponential form. So this is the rectangular form. In exponential form, our form is z is equal to r e to the I theta, and we wanna fill in r and theta. So we look at our polar form up here, R was 7. And then the one catch on here, and again, I'm sorry, correction from last class, is anytime we use this exponential form, we should have this angle in terms of radians. So 210 degrees is 7 pi over 6. Right, that's 1 whole pi plus 30 degrees more, which is 1/6. So 1 plus 1/6 is 7/6. Any questions on this example? Any questions? Okay, so what we have for the remainder of this section is a couple more theorems of working with complex numbers that are in polar and exponential form. These ones are listed on your formula sheet, so you don't need to memorize these last two sets of formulas. But you should know how to work with them. So you'll definitely have a question on your exam that asks you to work with them. So if we want to form products and quotients of complex numbers in polar form, so products and quotients means multiplying and dividing complex numbers. Here, what we're going to do is take a look at two complex numbers. I have z is equal to r cosine of alpha plus I sine of alpha. And then a second complex number I'll call w. And we'll just use some different variables here. So s cosine of beta plus I sine of beta. Okay, so here we have two complex numbers. Okay, so we have a theorem that says if we multiply these two complex numbers together and they're in polar form, their product is just r times s times cosine of alpha plus beta plus I sine of alpha plus beta. And if we do division of these complex numbers, so we form the quotient z over w, that's going to be equal to r over s times cosine of alpha minus beta plus I sine of alpha minus beta. Okay, so again, these two are listed on your formula sheet. But the derivation of these is actually really simple. I'm not going to write it out today. It's in the textbook. The proof of this comes from complex numbers being in exponential form. So if we had these two complex numbers written in exponential form and we multiplied them together, we would multiply the numbers out in front, and then the exponent would be the sum of the angles. Okay, so once we put this into exponential form, these follow really quickly. For the product, again, we'd have the quotient, for the quotient here, z divided by w, we'd have the quotient of the coefficients in front. And then since we have w on the bottom, our exponent would be a subtraction, and then it would just go over to a polar form here. Okay, so this is just based on the exponential form. It's a pretty easy proof, but I don't really think it's necessary to go through all of that for you guys. So what you should know is how to apply this formula. So let's just do one quick example here. So here we have two complex numbers. The first one is z is equal to 3 cosine of 20 degrees plus I sine of 20 degrees. And w is equal to 5 cosine of 100 plus I sine of 100. Okay, we have a part A and part B. Part A, we're asked to find z times w. Okay, so our theorem up above says that if we multiply these two complex numbers together, we should multiply this 3 times this 5, so that goes out in front. And then we have cosine of the sum of these two angles, so 20 plus 100 plus I sine of 20 plus 100. So 3 times 5 is 15. 20 plus 100 is 120. And there we go. So that was pretty simple. You should remember if it asked you, so this is called polar form. There are two other forms. There's also a rectangular form and exponential form. So if you're asked to put this in rectangular form, I believe your homework problem asks you to leave it in the polar form like this. If you're asked for a rectangular form, you would evaluate these two things and work it out. If we're asked to put it in exponential form is re to the I theta, and theta has to be in radians. So in exponential form, we would have 15e to the I theta, and this angle theta needs to be in radians, so that's 2 pi over 3. So just pay attention on your homework. On polar, sometimes you'll have this in terms of degrees or in radians. You could use either. So if it asks you to give your answer in radians instead of 120 here, you would put 2 pi over 3. Okay, so just pay attention to the terms on your homework. Any questions on that? Okay, part B. Let's find Z over W. So our theorem up here says Z over W is going to be R over S, so 3 over 5 times cosine of our first angle minus the angle that came from this complex number in the denominator. Okay, so we got 3/5 times cosine of 20 minus 100 is negative 80 degrees. And we still have a little bit of more work to do here. So the first thing is, regardless of if we're in polar or exponential form, this angle theta should always be positive. It should always be between 0 and 360. Okay, so if we look at where negative 80 is right here. What we want to do is find the equivalent positive angle. So remember on your homework, you had those questions that asked you to find other ways to get to some number in our polar plane or complex plane in polar form. So if this is 360 minus 80 gives us 280. So the positive angle here is 280. So we should never have a negative angle in either polar or exponential form. Now, this is polar form in degrees. If we were asked to put this in radians, we would need to do the conversion. If we were asked to put this in exponential form, we absolutely have to put theta in radians. So 280 isn't one that we can easily do in our head. So remember, if you can't easily do this in your head, what we do is we take 280 and we multiply by pi over 180. Okay, the first thing I noticed here is these both have a factor of 10, so we'll cancel it out. And then I need to reduce 28 over 18. So 2 goes into 28 14 times, and 2 goes into 18 9 times. So I got 14 pi over 9. Okay, so if we were asked to put this in radians, it would be 3/5 cosine of 14 pi over 9 minus I sine of 14 pi over 9. If we were asked to put it in exponential form, that is r e to the I theta with r and theta filled in. Any questions on this? Okay, our next theorem is just kind of an extension of doing this product theorem, and it's showing us how to take a complex number to an exponent. Okay, and I did not speak French, so I apologize ahead of time if I don't get this exactly right, but this is called de Movieres theorem, Okay, and what de Movieres theorem allows us to do is to take a complex number in polar or exponential form to take it to an exponent. So if we have z is equal to r cosine of theta plus I sine of theta, or in exponential form, we have r e to the I theta. If we take a complex number to the power n, de Movieres theorem says that this is equal to r to the n times cosine of n theta plus I sine of n theta. And if it's in exponential form, we have z to the n is equal to r to the n times e to the I to the n theta. So again, this is actually just an extension of the last theorem where we have a product taken over and over again n times. Okay, but this is referred to as de Movieres theorem. He's the mathematician who invented this or who proved it. So I'm not going to do the proof because it comes directly from the last one, but let's just do two quick examples where we see how this is used. So the first one here, we're asked to write the complex number in standard form, a plus bi. Okay, so remember standard form of a complex number, a plus bi. Sometimes you see this as x plus yi. The a and the b and the x and the y, those are just dummy variables. So standard form means rectangular form. That's typically how we see complex numbers. So we're given the complex number 5 cosine of 70 degrees plus I sine of 70 degrees. And we're raising this to the third power. So lining this up with our polar form up here, this is r, this is theta, and this is our power n. So de Movieres theorem says that if we take a complex number in polar form to an exponent, that's just equal to r to the n. So that's 5 cubed times cosine of n times theta, so 3 times 70 degrees, plus I sine of 3 times 70 degrees. And now we just need to simplify this and get it into this standard form. Okay, so 5 cubed is 125. 3 times 70 is 210. Okay, this is polar form. If we were asked to leave it in polar form, we would be done at this point. This asked us to put it into standard form or rectangular form, a plus bi. So the next thing we need to do is evaluate cosine of 210 and evaluate sine of 210. So get values for those. These boil down to the 30, 60, 90 triangle. So we can do this by hand, or you can use a calculator if you'd like. So cosine of 210 is negative root 3 over 2. Sine of 210 is negative 1/2. The last thing we'd want to do is multiply this out. Since we're asked to put it in standard form, a plus bi, we want to make sure we multiply this out. And you see here, this b is in front of this I, so we want to keep that in mind too. So I'm going to distribute this 125 to both of these terms. I get negative 125 root 3 over 2 minus 125 over 2 I. And we weren't asked to put this in exponential form, but if we were, we'd have r being 125 and theta was 210, so we need to convert this to radians and then plug it into exponential form. Any questions on this one? Any questions? Okay, I got one more example of how to use de Movieres theorem, and it kind of puts together everything we've done in this section into one, I hate to say big example, but big example. So we'll kind of use everything we did in this section. We'll start with something in rectangular, we'll convert to polar form, we'll apply de Movieres theorem, then we'll put it back into rectangular form. Okay, so we'll do some conversions back and forth to get some practice. All right. So last one for the section, let's write the expression. In the form a plus bi, and we're given 1 minus I to the 9th. Great, so there's two ways of doing this problem. The first way is by actually writing this out 9 times, right? We could write 1 minus I times 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 1 minus I 9 times. And we would have to start by evaluating each of those two products, working that out, and then we would expand it to all nine factors there. That is not elegant, and that's very cumbersome, right? It takes us a lot of work. So what I'm going to do instead is I'm going to convert this to polar form, which this will be good practice for us to put this in polar form. And then I'm going to apply de Movieres theorem, which allows us to take a complex number to a power really easily. And then since this wants me to have it in the form a plus bi, then I'll put it back into rectangular form. Now, in all my years of teaching this class, I've been teaching this class for over 10 years. Usually I have classes of like 200 students. In all my years of teaching this, I've always challenged my students. In the time I'm doing this, which sounds like a lot of work, can you do 1 minus I to the 9th by hand? And in my more than a decade of teaching this class, I've never had somebody beat me. So if you want to try this at home or on your own time and actually write out 1 minus I times 1 minus I times 1 minus I times 1 minus I 9 times, and see if you can beat me on this or time yourself, go for it. I'd be really impressed. Okay, so the first thing I'm going to do is convert this to polar form. So here x is 1 and y is -1. So in polar form, we need to come up with r. R is the square root of x squared plus y squared. So we have the square root of 1 squared plus -1 squared, which is square root 2. Okay, for theta, we know that theta is equal to inverse tangent of y over x. Y here is -1 and x is +1. Let's just check what quadrant this is to make sure we don't need to add 180. So this x is 1, y is -1, so here's 1, -1. So we're in the 4th quadrant, so this will work out. All right, if you punch this into your calculator, inverse tangent of -1, you should get -45 degrees. Now what I'm going to do is I'm going to use the equivalent angle in radians because that's easier to multiply out. So we know our polar form is r cosine of theta plus I sine of theta with r and theta filled in. Okay, so I just figured out up here r was square root 2. And for theta, this makes sense, right? Here's our 1 root 2, so this is -45 degrees. I'm going to use the equivalent positive angle in radians. So in radians, this is 7 pi over 4. Okay, so this is 1 minus I. 1 minus I. Now, our goal is to take this to the 9th. Take this to the 9th. So de Movieres theorem says that taking this to the 9th, we would get square root 2 to the 9th times cosine of 9 times 7 pi over 4 plus I sine of 9 times 7 pi over 4. Okay, so square root 2 to the 9th, you could either think through this, square root 2 times square root 2 times square root 2, 9 times, Or you could remind yourself that the square root is the 1/2, so this is 2 to the 9 over 2. However you want to do this, you should get 16 root 2. Here I have cosine of 63, right? Multiplying this out, pi over 4 plus I sine of 63 pi over 4. Now what we want to do to get it into rectangular form, we want to evaluate these and simplify. So if you have a calculator, you could put these in your calculator, but we'll do it by hand. So 63 pi over 4, if we do the division here, 63 divided by 4, this is 15 3/4 pi. Okay, so let's draw out this angle. We know how to do this by hand. So we have 15 pi. So here's 1, 2, 3, 4. We notice that every odd pi, we're back here. So 15 pi should bring us here. And then 3/4 more would be here. So 3 pi over 4, we know that has a 45-degree angle in here, and our sides are 1, 1, and root 2. So cosine of 63 pi over 4, cosine is just adjacent over hypotenuse, and sine is just opposite over hypotenuse. And in the fourth quadrant, we know sine is negative and cosine is positive. Or, of course, you're welcome to use a calculator for the exam. So here we get cosine is 1 over root 2, positive in the fourth quadrant. And sine is negative 1 over root 2, and sine is negative in that fourth quadrant. Our last step would be to multiply this out. So the good thing here is these root 2's are going to cancel. So 16 root 2 times 1 over root 2, we just get 16. And then 16 root 2 times negative 1 over root 2, the root 2's will cancel, so we get minus 16i. Anybody else do this the long way and get the same answer as me? You guys are probably thinking that did look like the long way. Okay, so what we figured out here was that 1 minus I to the 9th, that was our original problem, is equal to 16 minus 16i. So that's pretty cool. If we actually multiply out 1 minus I 9 times, we get 16 minus 16i. Now this problem didn't ask us to put it in exponential form, but let's just say we were asked to do this in exponential form. So let's just bonus here. If we put something in exponential form, that's r e to the I theta, and we want to fill in r and fill in theta, we would pull these off of this polar form here. So off of this polar form, r was 16 root 2. And theta, we need to make sure we use theta that's between 0 and 2 pi. So this was our picture. So we're looking for this angle, which is 7 pi over 4. Oops, I wrote a cosine in here. Let me start this over. I have it right here, and I wrote something totally different. So r was 16 root 2, e, I, and then theta, we'd use this angle, which is just 7 pi over 4. So these two are equivalent to this.